Hey everybody in Calc BC, welcome to Unit 8. Unit 8 is a pretty short unit. We are finished almost everything in AP Calculus BC. The only things that we have left are two lessons from College Board's Unit 7 on differential equations. So we're going to cover those over the course of what we're going to call 3 different lessons in our short unit, and that's going to cover approximating solutions using Euler's method and logistic models with differential equations. So today's lesson is 8.1, Euler's method. And to be more specific, Euler's method provides a procedure for approximating a solution to a differential equation or a point on a solution curve. So we've just talked about approximating values using series for a whole unit. Now we're going to talk about what if we're given a differential equation, how can we approximate a solution in that context. So we'll study that, and let's head over to the notes. All right, so here we go, 8.1, Euler's method. A differential equation in x and y is an equation that involves x, y, and a derivative of y. For example, down here, dy dx equals x over y. So you learned in AP Calculus AB and earlier this year how sometimes we can separate the variables and then use integration in order to, backtrack and find the original function, right? Now, depending on the form of the dy dx, if it has x and y in it, sometimes it's not separable, and sometimes solving a differential equation analytically can be difficult or even impossible. However, there are two other approaches that can help with this. One of them is using a slope field, which you've talked about before, and a slope fields use a graphical approach. And that helps you just kind of imagine what the curve might look like. And the second is Euler's method, which we're going to learn today. It's a numerical approach that can be used to approximate the particular solution of the differential equation. Euler's method. Okay, so we're going to go through exactly what all this means, but first I'm just going to read you the definition. Suppose that you have a differential equation involving x, y, and the derivative dy dx. Euler's method is based on tangent line approximation. Y times x 0 plus delta x is approximately y times x sub 0 plus y prime times x sub 0 times delta x. That's a little complicated. It'll make sense as we go. Let's just skip ahead to example 1. Given the differential equation dy dx equals x over y, let y equals f of x be the particular solution to the given differential equation with the initial condition f of 4 equals 1. So we have a derivative and we have an initial condition that the function, not dy dx, but f of x, when x equals 4, y equals 1. So we're going to use Euler's method starting at x equals 4 with 2 steps of equal size to approximate f of 5. Show the work that leads to our answer. So let's imagine that somewhere over here, we're going to try to recreate this function. We don't know what it looks like right now. The only thing we know that when x is 4, y is 1. So I'm going to label the axes here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, I guess to 4 there, and 4, comma 1. The only thing we know is that that point is on our curve. Now this technically is separable, so there is a way that we could come up with a formula, but we're going to use Euler's method here to approximate f of 5. So we want to know what is happening between the x values of 4 and 5. That way we can kind of guess where the point might be by the time we get here. There's going to be some sort of curve. It's doing something, but we don't know what the function is. We just know what the derivative is. So if we knew the derivative at 4, at least close to 4, that slope would be pretty accurate, right? So we can figure that out. And what we're going to do is kind of split this region up into 2 steps. So we're going to use the slope at 4 to guess where a point might be at 4.5. And then we're going to use the slope at 4.5 to guess where the function might be by the time we get to x equals 5. The easiest way to do that is to create a table. So the first step in any of these is to find out what your delta x is. Delta x means change in x. And that is talking about like how big is each step. So how much are we going to be changing the x value to get to each step in our approximation pattern here. So the way to find this, and it's the same thing that you did back in, you know, the olden days when we used to do Riemann sums. We do b minus a all over n. And in this case, we're starting at 4, we're going to 5, and we're trying to do 2 steps. So it's going to be 5 minus 4 over 2. So our delta x ends up being 0.5, which, I mean, we could have figured out, right? To get from 4 to 5 with 2 steps of equal size, each step is going to have to be 0.5. Now we're going to make a table, like I was saying. So we're going to have an x and a y. We're going to have a dy dx. And then the last section, which is going to be a little bigger, is y plus dy dx times delta x. Okay, so the first x value we're going to start at is, you know, our starting value, which is 4. And since we're going to have 2 steps, we're going to have 2 additional rows in our table. So we're going to go from 4 to 4.5, and then from 4.5, we're going to go to 5. We know the first y value. The first y value is 1 that was given. So now what we're going to do is figure out what is dy dx, or what is the slope at this point. And we figure that out by plugging the x and the y into the derivative that's given. So it's going to be 4 over 1. So 4. And now what we do is we figure out, let's just pretend that from 4 to 4.5, the function had that slope. Where would the point end up? So let's try it. So if we start with the y value where we were, and we add the derivative for the duration of our change in x. So we're going to add the amount of the slope that corresponds to a distance of 4.5 or of 0.5 in the x direction. It's kind of like if you're doing rise over run. We're not going to go up 4 over 1. That would take us all the way to 5. So instead, we're going to go up 2 over 0.5, because that's going to be kind of like halfway to a whole unit, because we have 0.5 of a unit. Anyway, we just do 1 plus, this ends up being 2, so it's going to be 3. The 3 then becomes our y value in our next row. So now we're going to use the numbers 4.5 and 3, assuming that this y value is correct, which, you know, it's an approximation at this point, so it's not correct, but it's close. We're going to plug those into our slope formula to figure out what would the slope be if the point 4.5 comma 3 was on our curve. 4.5 divided by 3 is 1.5. So now we do the whole process again. So we have 3 plus, and our dy dx this time is 1.5. The delta x is always the same, it's 0.5. So we get 3 plus half of 1.5 is going to be 3.75. 3.75 comes down here to become our new y value. And look at that, we already found an approximation for f of 5. So therefore, f of 5 is approximately 3.75. Graphically, what this looks like is we started with 4 comma 1, then we got 4.5 comma 3. So we used that slope at 4 comma 1 and said, hey, if the slope goes in a straight line all the way to x equals 4.5, what y value do we get to? And the answer is 3. And then we say, okay, well, let's shift our slope now to better represent our function, since we kind of traveled a little bit. We plugged in the new slope, the new x and y value to get the slope, and now we got to 3.75. So we kind of shifted this way a little bit. So this becomes our Euler approximation. And this is what Euler's method always looks like. It just looks like a series of line segments that kind of slant a little bit each time until you get to the end of your approximation. All right, let's keep going here. Letter B. Find the particular solution, y equals f of x, to the differential equation dy dx equals x over y, with the initial condition f of 4 equals 1. So now we're going to actually do the work, which you did as part of calculus AB. Okay, so let's see what we got here. So we're going to have to separate the x and the y. So I'm going to move the y to the left side. So it's with the dy, and then move the dx to the right side. So we end up with y dy equals x dx. And then I'm going to integrate both sides. So we end up with y squared over 2 equals x squared over 2 plus c. And I have an initial condition 4, 1 to plug in here. So I have 1/2 equals 4 squared over 2 plus c. We need to find c. So it becomes 1/2 equals 4 squared of 16 divided by 2 is 8 plus c. Subtract 8 and we get negative 15 over 2, or negative 7.5 equals c. So we get y squared over 2 equals x squared over 2 minus 15/2. So then our next goal is to solve for y. So let's keep going. And I'm going to multiply everything by 2. We end up with y squared equals x squared minus 15. So y equals plus or minus the square root of x squared minus 15. And f of 4 is a positive 1. So if we plug in 4 here, we get 4 squared minus 15 is 1. Square root of 1 is positive. Or it could be plus or minus 1, but we want our answer to be positive. So I would write since f of 4 equals 1, y equals positive square root of x squared minus 15. So we found the particular solution. And then we want to find f of 5. And 5 squared is 25 minus 15 means square root of 10 is our answer, which is approximately 3.162. So we got 3.75. The real answer was 3.162. So if we went back up here at 5, we were actually at 3.162. So our curve probably actually did something like this. We'll call that the actual curve. So you can see that the further we went in our Euler approximation, the further we got away from the actual curve, but it's still a decent approximation. Part C, the error in using Euler's method is the difference between the approximate value and the exact value. What was the error in your answer? So to find the error, we would do the actual answer minus our approximation, which ends up being approximately 0.588. And let's see, what was the error? 0.588. How could you produce a smaller error using Euler's method? The rule is the more steps that we use to approximate, the better that our approximation is going to be, because the more times we're going to take slope into account. Okay, so I will just say produce a smaller error by using more steps. All right, we got 2 more examples to go, so let's keep going. Next question. Given the differential equation dy dx equals x plus y, let y equals f of x be the particular solution to the given differential equation with the initial condition f of 4 equals -1. This time, because we have x plus y, we couldn't separate these variables even if we wanted to. It's not separable. It's stuck that way. That we can't ever move the y to the other side, multiplied by the dy, and leave the x there, multiplied by the dx. It doesn't work. But let's use Euler's method starting at x equals 4 with 2 steps of equal size to approximate f of 4.2. So first things first, we need to find our delta x. It's always b minus a over n. So in this question, we're going from 4 to 4.2. So it'll be 4.2 minus 4 divided by 2, because we want 2 steps. And so it's going to be 0.2 divided by 2, or 0.1. So let's make our chart. The top is always the same. X, y, dy dx, and y plus dy dx times delta x. So this time we're starting at x equals 4. We're using 2 steps of 0.1. So it's going to go from 4 to 4.1 to 4.2. All right, let's fill in our chart. So we started with 4, -1. We plug in 4 and -1 for x and y in the dy dx. We're going to end up with a dy dx of 3. And then we're going to have to do -1 plus 3 times 0.1, which will give us -1 plus 0.3, which is -0.7. So that becomes our new y value. 4.1 minus 0.7 is 3.4. So now we have -0.7 plus 3.4 times 0.1, which is 0.34 minus 0.7 ends up being -0.36. So that's our final y value, and that's our approximation. So we have f of 4.2 is approximately -0.36. Okay, last question. This time a bunch of the derivatives are given. So the table gives selected values for the derivative of a function g on the interval from -1 to 2. If g of -1 equals -2, an Euler's method with a step size of 1.5 is used to approximate g of 2, what is the resulting approximation? So we're going to start, of course, with our delta x. And it tells us already the step size. So this time the delta x is the 1.5. And we're trying to get to 2. So let's see what we can do here. So we need an x, a y, a dy dx, and y plus dy dx times delta x. So we are starting with g of -1 is -2. We're using a step size of 1.5. So -1 plus 1.5 is 0.5. 0.5 plus 1.5 is 2. And we were trying to approximate g of 2. So that's where we're going to stop. Okay, so in this notes, every single one of these examples has had 2 steps. Just want to be clear that that's not always the case, but it ended up working out that way this time. So let's follow through with our pattern here. When x is -1, we're given that the derivative is 2. So now we have -2 plus 2 times 1.5. So we have -2 plus 3, which is 1. So the next y value is 1. When x is 0.5, we're given right off the bat that the slope is 1. We don't have to kind of use the y value this time. We're just told the slope is 1. So we apply that. 1 plus 1 times 1.5 is going to be 2.5. And we get to 2.5, and that's the end. Okay, because we got our approximation at x equals 2, which is what we wanted. So the answer is D, 2.5. And that's a sample multiple choice question from College Board that could be similar to something that's on the AP exam. So I wanted to show you something like that. There are a couple other variations of ways that Euler's method might show up. You might see something in the worksheet, but we'll continue to see examples throughout this unit. So thank you very much for watching. That's it. Have a great rest of the day. Thank you.